Brief example on how to conduct linear optimization and linear modeling in Python. We can do linear programming in Python using the SciPy package. This will comprise the optimize package, and as part of that we got access to the linprog function. The linprog function allows us to conduct linear programming and solve linear optimization problems as the one shown here as an example. So you see here I have an exemplary problem stated in scalar syntax. We have an objective function with two coefficients and two optimization variables. We have two constraints in the less than or equal to direction. And we basically are optimizing in the continuous space. We also have the constraint of non-negativity. Now, if we want to solve this problem, which it's a maximization problem, we need to turn it into a minimization problem, as this is the default problem form that linprog is using or is assuming. And we can do that by simply multiplying the objective function with -1. Then we need to describe the problem with vectors and matrices. So we need a cost vector with the coefficients of the objective function. We need a function with, we need a vector with all the variables, so all of our optimization variables. Then we need a matrix with all the coefficients of our constraints, and we need a constraint vector with all the values of our constraints. And then we also need to describe the lower and upper bounds of our optimization variables. In this case, we do not have any upper bounds, but we do have a lower bound, which is 0. So if we go down, I'm showing here how to solve this example using the linprog function in Python. And if you would like to, you can click the link in the video description and see it on your own on my blog. So the first thing I'm doing is I'm defining the cost vector. Now you see here, I'm writing -2 and -3. If you look at the original objective function, it was 2x1 plus 3x2. But this was a maximization problem. We still want to solve the maximization problem, but we have to state it as a minimization problem. And we can do that by minimizing over the same objective function, but multiplying it with -1. So basically, instead of +2 and +3, I have to write -2 and -3. I'm now defining the coefficient matrix with the coefficients of my constraints. So my constraints coefficients are 1, 1, 2, 1. I need a vector with the constraint values, which are, as you can see, 10 and 15. And then I need two tuples, one tuple for each optimization variable, and the tuple will have as first entry the lower bound and as second entry the upper bound. In this case, we do not have any upper bound, so I write none. Then I import the linprog function from SciPy, and I pretty much feed this information to it in form of parameters. So the first thing I provide is the cost function, then the coefficient matrix, then the constraint vector with the constraint values, and then a list with all the tuples that contain the lower and upper bounds for each optimization variable. And once I execute the linprog function, it will return an object. I save it here as model linear because this will basically be the solution to our problem. And as you can see, I can also print this the solution, and you will get it printed out in this form. So we can see now here the optimal solution. So this is the optimal objective function value. You can see the slack of the constraints. So you can see in this case, the first constraint is binding, and the second one has a slack of 5. And you can see the optimal point in our solution space here at the bottom of this printout. So x1 should be equal to 0, and basically everything should be put into the second optimization variable, which is x2. So x2 equals 10. That would be the optimal solution. Now the optimal value to our original problem, which was the optimization problem in form of maximization, is of course not minus 30 but plus 30. And the reason is, again, in order to transform it from a maximization problem to a minimization problem, we multiply it with minus 1. Now if we want to interpret the results, we of course have to multiply with minus 1 one more time. So the optimal solution is plus 30 and not minus 30.